So for my final project, I wanted to look at electric vehicle pricing analysis. A little bit about the data. It comes from an open source EV database called the Electric Vehicle Database that has 238 vehicles. The dataset that I used was curated from this and posted on Kaggle, which is just a small subset containing 103 observations and only 14 features per vehicle. These were the research questions I wanted to answer with my analysis, which will be posted on separate slides. And then as we load in the data, this is what it looks like with the 14 features, one of which is the target variable price euro, and the remaining are fairly split between categorical and numerical variables. So a couple that I had to look up the meaning for are efficiency, which is essentially saying the number of watt hours that it takes to move the vehicle 1 kilometer, and fast charge is the number of kilometers the vehicle can travel after an hour of charging, and rapid charge is a Boolean field, so if it's yes, then fast charge will be populated. If rapid charge is no, then fast charge will not be populated. And segment is another way to look at body style in terms of classifying how large the vehicle is. Looking at the causal loop diagram, I thought that all features would have a positive relationship with price, with the exception of acceleration and efficiency, which the lower the number, the better for these. So I thought it would have an inverse relationship, so the lower the efficiency value, so the more efficient a vehicle is, the more expensive it would be, and the faster the car accelerated, so the less number of seconds it took to accelerate to 100 kilometers, the more expensive the vehicle would be. Next, we can look at the distribution of the target variable, which is quite skewed right, since there's a long, narrow tail there, and the median is less than the mean. So before looking at the EDA, I wanted to touch on the research questions to give a bit of context. So Tesla produces the greatest number of car models, 13 out of the 103 observation, and there are 33 unique brands, of which 7 brands represent 52% of the cars in this data set, which I thought was also interesting to look at. Next, Tesla makes the most expensive car at 215,000 euros. The next question, the car with the highest average price was made by Lightyear, which only produces one model, hence the high average, since it is one of the most expensive vehicles. Next, which car has the fastest acceleration from 0 to 100 kilometers? And the fastest 3 are Tesla models, all quite expensive. Looking at the car with the highest efficiency is one of the most expensive vehicles. It's that Model 1 by Lightyear. This was also interesting to look at because the next most efficient vehicles are all very comparable in terms of efficiency, but drastically cheaper than the Lightyear Model 1. So the next research question was, does a difference in powertrain affect the range, top speed, and efficiency? I found that overall powertrain has a moderate relationship to these variables. The strongest one is between powertrain and top speed. So on average, I thought that there was powertrain had somewhat of an impact on the range, top speed, and efficiency, but it was not very strong. The final research question I wanted to look at was which factors have the most influence on price. So for this, I looked at the R-squared and adjusted R-squared values and came up with the 5 top features that explain the greatest variance in price. So for those, it would be acceleration, top speed, range, fast charge, and segment. Next, we can dive into the data a bit. This was interesting to look at the different plug types for EVs because I was not familiar with it before. So this is what the different plug types look like between region and then also current type. So we can see that this CCS type 2 plug makes up a majority of these models. Unfortunately, the correlation statistics was not very high for this, so I did not end up using it in my final model. We can look at some of the variables that had the highest correlation with price, top speed being one of the strongest. It has a very strong linear relationship. since the R squared and adjusted R squared were very similar and both above 0.8. Next is acceleration, which had a stronger nonlinear relationship than a linear one, though fairly strong association between price and acceleration here. Next, looking at fast charge. So this one had a little bit of a stronger correlation than acceleration. However, again, it looks like a stronger nonlinear relationship between these two variables. Next, we can look at range, which had a fairly strong relationship with price euro, but again, it looks like more of a nonlinear relationship between these two variables. Finally, we can look at segment, which surprisingly had a pretty strong correlation here, especially since the distribution was a little skewed. However, just looking here, we can see there's a pretty positive relationship between the size of the vehicle and the price, so hence the strong linear positive relationship. Next, we can look at building a model. So for my null model, I decided to include all features. So including these categorical features resulted in 172 total columns. And when I ran the model, it came back with an R squared of 1, which I thought was a little odd, especially since the sigma values did not calculate as numbers. So to look into this a bit further, I looked at the residual plots and found that for all of the numeric variables, it looked very similar to this, where it was right around 0, so not much residual value there. So going back to the drawing board, I decided to take out the model variable from the null model, that is, and that came back with a little bit more promising results. It actually gave me a sigma range and an R squared that was slightly less than 1, although the upper bound of the 95% confidence interval was still 1 for this R squared. When I did the 95% confidence interval for sigma, it did not calculate, so I ended up using max error as my other evaluation metric in addition to R squared. And then when I did the 95% confidence interval for the mean R squared of the null model, I ended up getting 0.535 to 0.762. And then for the mean max error of the null model, I got negative 45,931 to negative 27,765. So moving on to looking at the learning curve, I found that adding more data would not help improve the model, given that the curves flatten out with the full training set. So with 20 to up to about 40% of the training data, it remains constant, then it drops, and then after about 65 or 70% of the training data is used, then it returns back to the baseline performance. So in order to create an improved model from the null, I decided to look at the residual plots of the numeric fields. And I found that, there was some scattering here, but overall the distribution looked fairly good. Nonetheless, I decided to see if any transformation of these variables would result in a better model. So first, I took the square root of these, which produced a bit more scattering and some noise. So next, I looked at the inverse, which again doesn't look too much better. There's still a bit of scattering and spread here. So then I decided to square each of the fields, again not looking quite as good as the non-transformed variable. And then finally I took the log of these variables, which again the spread of the residuals was a bit higher than the non-transformed variables, so I didn't end up using any of these transformed variables in my improved model. Instead, I decided to look at the correlation for each of these variables with price, and I decided to remove all variables with less than 0.2 r squared. So the variables highlighted in green here are the ones that I kept in my improved model. And running the improved model, these are the stats that I got back. So the summary showed that the sigma value had a range from 5929 to about 1300 with a mean of 11,606, and the r squared was about 0.91. When I ran a 95% credible interval on the r squared, I got 0.155 to 0.9647, which was a bit narrower than the spread of the r squared for the null model. And then for the 95% confidence interval of the max error, I got negative 137,665 to negative 6,866. So this had a bit wider of a range than the null model. And then the actual 95% confidence interval for the mean r squared of this model is 0.597 to 0.776, and then the mean max error for this model was 52,410 to negative 26,695. And the name of this model just comes from the number of iterations that I went through to actually create it, hence Model 7 is the name. So if we compare the models, this is first looking at the difference in mean r squared values. So the improved Model 7 right here on the right, and then the null model on the left, and then the difference of the posterior distributions is on the right. So it's just taking the null model r squared posterior distribution minus the improved Model 7, and then this is what we're left with. So again, I did the same thing for the max error between the null model and the improved model. And then this is the distribution of the difference. And then finally, evaluating those, I decided to do a rope looking at the what's the probability that the mean or difference in mean of r squared is greater than 0.05. So I decided to look at a difference of 0.05 for the r squared as a definition of a true difference in mean r squared between the models, and found that the likelihood of that is only 16.5%. And then to define a true difference in the max error, I went with 2400 because that was the difference in the sigma values between the null model and the improved model. And so I found that the probability that the difference in mean max error between the null and improved model is only 47.9%, or 0.479. So overall, I found that, you know, there isn't a very believable difference in these models given the ropes. So overall, they're pretty comparable in terms of accuracy. And that is what I found for the pricing analysis of EVs.